Hey, physicists. So now that you have done your conclusion from the lab that with the cart and the pulley, we are going to try and put this all together. There were two questions that we were trying to answer in that lab, and each of you only got to do one. So we need to kind of put everything together and establish a pretty important physics concept from the lab that you did. So to get started, make sure that you have paper out so that you can take some notes. This is going to be your opportunity to get formal notes on this. So go ahead and pull that out. If you need to pause, that's great. And then come back. And once you're back, we're going to take a look just at you remember the way that we started out our lab. We were reminding ourselves from last trimester that if the net force on an object is zero, right, we said that the object's acceleration is indeed zero. That's a pretty big and pretty important thing. We also said that if the net force on an object is not zero, based on what we had observed last trimester, we knew that the object's acceleration was brilliantly not zero. That's a pretty important deal as well. Just want to make sure everything is still good. Okay. The trouble with that is that not zero includes a whole lot of things, and we want to know what the actual value of the acceleration was. And that's the whole point of what we did in the lab that we worked on this week. So we're going to put this all together here. If you recall, there were two questions that we were trying to answer in the lab. So the first question, I think I called it question A, was if we've got our cart here, and I think we called that cart A, and it was sitting on a track with the pulley and the string, and then we had these masses, these washers down here. Question A was, how does the mass of the cart affect its acceleration? And hopefully you found, if you were working on this one, that as the mass of cart A goes up, that the acceleration of the system actually goes down. Okay, so again, as the mass of cart A goes up, the more of those little pieces you put on the cart, the acceleration goes down because it takes longer for it to move. If you graph that, we see something like A, which is our dependent variable over here, and the mass of cart A, which is our independent variable on the x-axis. We find, excuse me, that the graph looks something like this. Okay, this actually happens to be what we call a hyperbola. If you know that from math class, awesome. If you don't, that's totally fine. No worries and no judgment. What we can say from this is that A is proportional to, this little kind of funny symbol right here means proportional to. It means that A is proportional not to M, because again, as M goes up, A actually goes down. It looks like this. It actually looks like 1 over the mass of A. And if you look at the proportionality that I've just written down right here, if you look at what happens to the mass, if the mass goes up, that means that denominator gets bigger. And if the denominator gets bigger, that means that the whole fraction gets smaller. So this is the first piece that we needed to know. So those of you that did question A, you figured out that first piece. The second question that we asked, or the second question that we investigated, was what happens if you increase the mass of the washers or the things that are pulling? And hopefully you can recognize that if I increase the mass of those washers, that's really increasing the tension on the string. And therefore, if we hop over here to, this is also from that introductory sheet. If we hop over here, we can see that in the x direction on cart A, the only thing pulling on it is Ft. So as Ft goes up, that means that the net force acting on object A also goes up. So if I hop over here, I'm going to do question B. Keep skipping letters here. T-I-O-N, question B. The issue was we increased the mass of B. I'm going to suggest that as we increase the mass of B, really we're increasing the tension force. So mass of B, if mass of B goes up, that means that the tension force pulling on A, Ft, also goes up. And I hope that what you found in this experiment was that as the tension force goes up, so does the acceleration. This is the key, okay? So if we sketch that graph, And I'm going to go ahead and put FT here, although if you were doing the conclusion for question B, you probably would have written the mass of B, and that's 100% fine, but I'm just kind of extrapolating through to get the physics all set up for you. FT is on the x-axis. I'm going to put A on the y-axis, and hopefully you found, as I said, that as the tension force goes up, the acceleration goes up. In this case, then, the proportionality is a little bit different. This case, the acceleration is proportional to the tension force and therefore the net force acting on cart A. Because again, I'm just going to hop back here just so that you can make sure you see it. There is no net force in the y direction. The net force in the y direction is 0. It's not accelerating up or down. But the cart A was accelerating in the x direction, and the only thing pulling on it was that tension force. Okay, so we can say that the acceleration on the cart is just proportional to the net force acting on the cart. So we've got these two proportionalities, and those two proportionalities build one of the most well-known rules or laws in all of physics. Okay, we're going to take them here together and put them in one big statement. Okay, so I've got A being proportional to two things. Here it comes. So I've got the acceleration is proportional to 1 over the mass. So it's the mass of the system being whatever things are accelerating. And I've got A is also proportional to the net force. So I'm going to change that 1 to an F net. And I'm going to set that as an equal sign. This right here is the big deal. This is why you came to school on a Tuesday right before Thanksgiving, right here. This is it. The acceleration of a system is equal to the net force acting on the system divided by its mass. If the net force equals 0, well, 0 divided by anything is 0, then that means that the acceleration would equal 0. Hey, look at this, look at this. Oh my gosh, that's exactly what we said here, right? That's so cool. And if F net is not equal to 0, now we know the acceleration is not equal to 0, but indeed the acceleration is equal to that net force divided by the mass, meaning that if I push with a certain force, the acceleration of that object is going to be dependent not only on the force, but also on the mass. This stuff right here is known as Newton's first and second law. What do I mean by that? This is really the first law. This is really the second law. But I believe, and I hope that you can see that really they are one in the same. Okay, so that's it. That's the big deal, the big important thing that you're here to do today. There are a couple of problems that I want you to work. They're up on the slides. And so go ahead and work on those between now and December when we see you again, right after Thanksgiving break, and then we will move on from there. I hope you guys have an awesome break, and we will see you soon. Take care.